Hello, welcome to the video. I'm Tsai-Shien. In this video, I'm going to present my new project named Video Alchemist, which focuses on multi-subject, open-set personalization for video generation. Our paper has been accepted to CVPR 2025, so hope to see you in Nashville in this summer. This is a collaboration project with Alexander, Willy, Yuwei, Quote, Ivan, Kafir, Junyan, Mingxuan, and Sergey. So let's start from a quick overview. We are living in an era that the state-of-the-art text-to-video models like Sora, VO3, and Snap Video has already been able to generate impressive videos, like a woman rides a dinosaur on the field. However, it would be more exciting if the model could generate your female friend riding your favorite dinosaur on a field with a volcano behind. To achieve this ambitious goal, in this video, I would like to introduce Video Alchemist, our video model that supports the personalization of multiple and open-set subjects for both foreground and background objects. Here are more samples generated by our Video Alchemist. The example here include different scenarios of multi-subject interactions. For example, a person talks with another person sitting in a meeting room specified by the user. Another sample shows a woman with a specific suit sitting in a personalized old-school living room. The third sample is a sci-fi movie setup with a launching rocket and an UFO on the surface of the moon, which of course cannot be filmed in a real-world scenario. We show that our Video Alchemist is able to synthesize natural motion while preserving subject identity and background fidelity. Moreover, through our background conditioning, you can now bring your favorite pet dog traveling all around the Earth or even on the moon. Next, before I dive into how we make Video Alchemist work, I would like to summarize how the previous methods achieve image or video personalization. In the early personalization methods, people usually adopt optimization-based methods where they learn a text token to represent a new concept. Textual inversion is one of the most iconic methods in this branch. Given a few images representing a new concept, they first learn a special token, like a star here, to represent a new concept, like the statue or cat here. It can then use this personalized text token in the prompt to generate images or videos with the new concept. But how it learns this special customized token? They usually freeze the pre-trained generator and text encoder and only fine-tune the tokenizer and embedding lookup dictionary to learn and insert a new word to represent this concept in the dictionary. Some other popular personalization models like Dreamboost and Custom Diffusion also use such optimization-based methods. However, a significant drawback of this method is that they require optimization to adapt a new concept. To fix this weakness, more recent personalization models use encoder-based methods which generate image or video using the embeddings of reference images as conditions. IP adapter is one of these works. On the top of generator, there's an image encoder to encode the reference image into features and inject them to the generator through the cross-attention. Hence, the model will generate the images or videos based on the reference images. Some other popular personalization frameworks, such as Instant Boost and Video Boost, also use encoder-based methods. In our framework, we also adopt the encoder-based method to eliminate expensive test time optimization and further extend it to more generic personalization. To learn multi-subject personalization, dataset is one main challenge. In this work, we introduce an automatic pipeline to collect a large-scale dataset for personalization. We construct our training dataset upon video and caption pairs. In the first step, we use a large language model to identify 3 categories of entity words from the caption, including subjects, objects, and background. In the meanwhile, we extract 3 video frames from the beginning, middle, and end of the video in order to capture the subjects or objects with different poses, facial expression, and lighting conditions. Next, we use this entity word to localize and segment the target subjects and objects from these video frames. For human, we additionally crop their faces to support face crop personalization. Finally, we extract a clean background image by removing the subjects and objects from the middle frame. Next, we introduce our model design. Our model is a latent space diffusion model, meaning that we generate a video by denoising the video in the latent space. Our model backbone is the DIT model, which is composed of a stack of DIT blocks. Each DIT block includes one multi-head self-attention, which is the main computation to denoise the video. The self-attention is followed by two multi-head cross-attention, where we inject the condition embeddings. In the first cross-attention, we inject the text embedding, which include the information of the text prompt. In the second cross-attention, we inject the personalization embeddings. However, for multi-subject personalization, a difficulty is that each entity word could be represented by one or more reference images. For example, we could input multiple images of this man to better describe his appearance. So how to connect the entity word and its corresponding reference image becomes a challenge. In this work, we propose a simple yet effective module to fuse the reference images and their corresponding entity words. Specifically, we first use a shared and frozen image encoder to encode reference images. Next, we retrieve the word tokens from the text embeddings, where the word tokens correspond to the entity words that each reference image represents for. We then concatenate the image embeddings and the word tokens and feed them into a linear projection to fuse both information together. Finally, we got multiple personalization embeddings where each feature represents how does the image look like and what entity word this image represents for. We then concatenate them together and inject them into video token through a cross-attention. Until now, we have a dataset and model backbone supporting the training of a generic video personalization model. However, in practice, we found that our model encounters severe copy and paste issue, where the model will directly replicate the reference image into the output video. Actually, we found that most of the encoder-based methods, such as IP adapter, also encounter such issue. This is because during training, we always input the reference image as conditions and learn to reconstruct this image based on itself. During inference, if a user designs different text prompts, the model will fail to generate a subject under unseen scenario. To explain this effect more comprehensively and technically, we found that our model tends to overfit on the training dataset. During training, when the reference image is high resolution, the model generates a large subject close to the camera. If the reference image is cropped, the model places the subject at the edge, causing it to be cropped by the video boundary. The model often replicates the subject's pose and lighting conditions from the reference image. If multiple reference images represent the same subject with similar poses, the model produces a subject with minimal motion. To mitigate the problem that the model learns to refer these undesirable properties of the image, we apply the corresponding augmentations and guide the model to focus on the identity of the reference images. That's all about how we build and train Video Alchemist. However, another challenge is that how to evaluate multi-subject personalization. It is challenging in two perspectives. First, there's no such benchmark dataset to test multi-subject personalization. Second, existing models usually evaluate the fidelity by computing the similarity between the entire reference and output image. However, such metrics fail to evaluate the fidelity for each subject independently. To address this challenge, we collect the benchmark videos from MSRPT dataset and annotate them with our personalization annotations. Next, to more accurately evaluate the fidelity of each subject and face, we segment the target subject or face from the video frame for the evaluation. I'm excited to announce that we have made this benchmark public. You can scan the QR code and download the benchmark from our GitHub repo. Here, we compare with the existing personalization models for the subject mode of our benchmark, where we input the entire reference image as the condition. Compared to the existing methods, our results closely match the input text prompt and reference image while showing natural motion and pose variation. Next, we compare with other existing personalization models for the face mode, where we only input the face crop as condition. our model still achieved better performance across most of the evaluation metrics. In a user preference study, we show that Video Alchemist achieved significantly higher preference in both quality and fidelity compared to all of the existing personalization models. To compare the performance of multi-subject personalization, we compare Video Alchemist with Pika. We show that our model can generate subjects with higher fidelity in most cases. In addition, thanks to our binding mechanism, we can apply the image condition to the right subject, for example, correctly putting this reference woman into the video. In the final experiment, we conduct an ablation study to evaluate each of the proposed modules. The experiments show that, first, we can achieve better subject fidelity by using Dino v2 rather than Clip as the image encoder. Second, we can correctly apply the image conditioning to the right subject with the usage of the word tokens. Finally, we can mitigate the copy and paste issue by applying the proposed personalization-specific augmentations. That's all about Video Alchemist, a video model supporting multi-subject and open-set personalization. To learn more, please visit our project page or GitHub repo. Hope to see you soon at another video.